Good morning, dear colleagues. This is my pleasure to give a talk at this 29th Davidov readings dedicated to 50 years of the Davidov soliton. And namely, this subject is the subject of my talk. It's a challenging task to shrink 50 years into 20 minutes, but I will try to do my best. So let me remind you that the first paper on molecular solitons, or Davidov soliton, has been published in 1973 by Davydov and Kislucha in Physica Status Solidi. And this photo shows Davydov in this very seminar room near the blackboard explaining the transport of amide-1 vibration in alpha helix. Let me remind you that a soliton is a solution of the nonlinear equation or system of equations in the form of a solitary localized wave, which propagates in the system without loss of energy, without any dissipation, and solitons interact between themselves without any change of their form and velocity, so they behave like quasi-particles. That's a general definition of a soliton. And Davidov's soliton, or molecular soliton, is a quasi-particle. It can be electron, hole, or molecular excitation, which is bound with the self-created deformational potential in a molecular chain. And this takes place due to electron lattice interaction. So this is, in fact, the polaron effect. Davydov and Kislucha were the first to introduce the concept of solitons generally in biophysics. And this was done to explain the energy transfer on macroscopic distances in biological systems. The situation is the following. The main energy unit in biological systems is the energy released in the hydrolysis of the adenosine 3-phosphate molecule into adenosine diphosphate molecule. This hydrolysis reaction is accompanied by release of energy equal to half of electron volt, which is in fact a tiny amount. It is only 20 times bigger than the energy of thermal vibrations at physiological temperatures. This subject was the main subject discussed in 1973 at the annual meeting of the New York Academy of Sciences, and there was no mechanism known at that time which could explain this efficiency of this transfer of energy. And the annual meeting concluded with the statement about the crisis of bioenergetics. And here comes Davydov with his background in solid-state physics. He says, well, this process can be facilitated by the macromolecules present in a biological cell, by macromolecules. They possess a regular structure, and due to this structure, electron states can form collective states, and moreover, the macromolecules are relatively soft, so the electron lattice interaction is important. So in these references, you can find more information on this subject. So the model which Davydov used was the following. Macromolecules, alpha helical proteins, as the best example. This figure shows the top view on the alpha helix, and this figure shows the side view. So the solid line corresponds to the chemical bonding along the helix, and we see three almost parallel hydrogen-bonded polypeptide chains. Polypeptide because peptide group is the group of HNCO. They are connected by hydrogen bonds, and one isolated chain is shown in this figure. The black dots are these peptide groups. The dotted line dash dotted line shows the hydrogen bonds between the nearest peptide groups. Sigma is electron lattice interaction, kappa is the elasticity of the hydrogen bond, and J is electron resonant interaction in the system. Such molecular chain is described by Crowley-Hamiltonian, which is sum of the quasi-particle Hamiltonian of the lattice, and Hamiltonian of their interaction. I will not write down here many equations, I just don't have time, but my main task is to bring you the main idea. So from this Hamiltonian, the system of equations, of discrete equations, can be obtained. And in continuum adiabatic approximation, this system of equations is reduced to the nonlinear Schrödinger equation, written in this frame. Here psi is the wave function of the amide-1 vibration of the excitation, and small g is the nonlinearity constant. The nonlinearity of the nonlinear Schrödinger equation is proportional to the square of the electron lattice coupling, inverse proportional to the exchange interaction constant and elasticity constant of the peptide group. The equation admits a very well-known soliton solution given by the hyperbolic cosine. The amplitude and width of this soliton are determined by the nonlinearity coupling constant, and the argument of this function is the running coordinate x minus vt, where v is the velocity of the soliton. So it propagates in the system as a running wave. This theory has been generalized to extended to explain the electron transport in macromolecules. From mathematical point of view, the system of equations turns out to be the same, and this electron transport occurs in the redox processes, which accompany all metabolism of biological systems, respiration, photosynthesis. In these redox processes, there is so-called electron transport chain in the membrane of mitochondria. So there are these green units, enzymes, which possess large molecular mass. Essential part of them is in alpha helical conformation, and there are other units with a small mass. So in each of these units, the electron transport takes place. When we speak about the electron transport, not about the excitons, the important aspect is statistics, the electron charge and spin of electrons. The study of this problem shows that the lowest energy state of two electrons is a singlet bisoliton. The energy of the bisoliton is binding energy is 8 times bigger than the binding energy of the soliton. In this singlet state, the spin is 0. It's not forbidden by the Pauli principle due to the spread of electron over few lattice sites. And this figure shows the charge distribution in the molecular chain of electron in a soliton state, this solid blue line, of electron in the bisoliton state, solid red line. We see that it is much more narrow and its maximum amplitude is much higher. And the dotted line dashed line shows the charge distribution in a triplet bound state. It's not two isolated solitons, but it is a triplet bound state. So when we looked at the soliton transport chain in redox processes, we concluded that in the enzymes, in the units of this electron transport chain, in which there is no local magnetic field, electrons should be transported by soliton states, by 2 at each step. While in the last unit, which is cytochrome C, cytochrome C contains ions, ferrum ions, which are fixed in the space, so that their magnetic momenta are fixed parallel. There is local magnetic field, and because of this local magnetic field, the singlet state is broken, and the electrons form a triplet bound state when their spins are parallel. In fact, this prediction has been concluded by the experimental measurements of the Hall effect. While in these 3 units, the electrons are transported in pairs, in the last one, one by one. Next thing I want to tell you is that very important feature of these structures of the molecules in biological systems, not only in solid state physics, but especially in the biology, is the role of the structure. To be short, brief, let us consider not isolated polypeptide chain, but alpha helix, which is 3 polypeptide chains, and take into account the helicity of the system, which means that the 3 peptide groups which belong to a unit cell are localized not in the plane perpendicular to the axis of the alpha helix, but this plane is under certain angle, so that there is a real helical structure. And it turns out that this structure is really very important. In the energy spectrum of the alpha helix, there are 3 energy bands: the lowest energy band, and the highest energy band, and the lowest energy band. There is no energy gap in the energy spectrum of the helix, and in the results there are different types of solitons formed in a system. Solitons formed by splitting from band bottoms of the highest energy band from the lowest energy bands, and because of the Young-Teller theorem, there is the hybridization of the electron states in the lowest energy bands, so that there is also entangled soliton state which has the lowest energy. This figure shows the charge distribution of electron or quasi-particle in each of 3 polypeptide chains. So we see that there is also internal structure of solitons. They are now more like breathers. And the red line shows the charge distribution per unit cell. So this is sum of the 3. So internal structure, different types of solitons, different energies. This panel shows the energies of different states. The blue line corresponds to the energy of the soliton in an isolated polypeptide chain using the same parameters for the alpha helix. The red line shows the energy of the soliton split from the higher upper energy band. We see that it has low energy. The yellow line corresponds to the energy of the soliton, which is split from the lowest energy bands. And finally, the green line corresponds to the energy of this entangled soliton state due to Young-Teller theorem. And for the parameters of the proteins it turns out that the energy of these lowest energy states is 50 times bigger than the energy of the soliton in an isolated polypeptide chain. So when we study the question of stability of solitons, question of their thermal stability, we have to take into account the real structure and be very careful using the parameters of the system for simplified models. Another important conclusion from this study is that the lifetime of the soliton in the entangled state in alpha helix is 3 orders of magnitude bigger than the lifetime of the soliton in an isolated polypeptide chain. This question is more, generally speaking, its importance is broader than the importance for biological systems only, because there is a large class of low-dimensional systems, not only biological macromolecules. These are conducting systems like the BDT salts structure, which is shown in this figure. Polydiacetylene, its structure is shown in this figure. Conducting platinum chains, other salts at moderate doping. In this system, and many others, but in these systems which I have cited in this slide, their parameters support existence of solitons formed by that mechanism. A new interest, the new wave impulse of interest to this subject has arisen recently due to synthesis of new low-dimensional materials and due to advances in nano and micro technologies based on complexes which include polymers, like conjugated donor polymer acceptor compounds, donor salt acceptor compounds, and many others. And in fact, in biological systems, in photosynthesis, the electron transport takes place not in isolated helix, but is transport chain of the electrons from a donor molecule to the helix to the acceptor molecule, and each unit in this charge transport chain plays a role of the acceptor for the previous unit and donor for the next unit. So this subject has been inspired by numerical modeling by Chris Ilbeck and Elvin Scott many years ago. This figure shows Elvin Scott and Davydov near the blackboard having hot discussions. Elvin Scott visited several times Kiev, and he played important role in spreading ideas, Davydov's ideas, to a broader audience. This figure shows Chris Ilbeck and Elvin Scott at this Scott-Russell aqueduct, where for the first time the soliton has been absorbed by John Russell Scott. And over there is my finger in 1995, when during the conference there was a reconstruction of launching the famous soliton in the Union Canal near Edinburgh. So let us consider the more complex system, which includes now a donor, helix, and acceptor. The Hamiltonian now will have the Hamiltonian of the donor, acceptor, and helix. The Hamilton of the helix, we remember by the previous study. This system is described by very large number of equations. So the easiest way is to study it numerically. And for numerical study, we have chosen the parameters of the protein molecules. And we consider the different types of coupling. So these parameters correspond to the steady state distribution of charge transport, which is shown in this figure. Different colors correspond to different strengths. This slide shows distribution per unit cell. And as the initial condition, we have chosen the following. We put electron at the donor molecule, so its probability of localization at donor equals 1, probability inside the helix and at the acceptor is equal 0, and launch numerical simulations. 25 numerical units of time later, we see that the probability of electron presence on the donor decreased to 40%, and there is formation of the decreasing exponent in the helix in the nearest end. 50 time units later, there is the further decrease of electron presence on the donor molecule, and we already see a very beautiful profile of the soliton in the helix. And this profile moves to the opposite end of the helix. So at time equal 200, there is some small amount, negligible amount of the electron presence in the helix and 35% on the acceptor. 500 time units, electron is transported with probability very close to 1 to the acceptor molecule, and the helix is in its equilibrium state. This process is described, very well described by the inverse scattering technique, which we have done many years ago, 30 years ago. Now, very important question is about the experimental confirmation of soliton existence. In my opinion, the most beautiful experiments have been done by Austin and colleagues and by others, which is connected with measurement of the lifetime of emit-1 vibration in systems which have identical primary structure and different secondary and tertiary structure. These are myoglobin, which is essential alpha helix, yellow protein, which is beta sheet, and in amino acid L-alanine, which is a unit of these two structures. And it turns out that, namely, in the alpha helical conformation, the lifetime is much bigger than the lifetime in yellow protein, and this is much bigger than the lifetime in L-alanine. Another experiments are electron transfer through H-bonded peptide assemblies. Then there is important measurement of 47 inverse centimeter vibration in cytochrome C oxidase, which in our opinion corresponds to the bisoliton. Coherence of electron charge transport in cytochrome C oxidase. Voss has concluded that this can be closely connected with the soliton mechanism. Quantum coherence of photosynthesis, hyperconductivity of the heterosystems donor polymer acceptor, about which I spoke in the last part of my talk. They are used in bioelectronic devices and with biomimicry technologies. There are many experiments. And in fact, there is even patent registered in United Kingdom, which is solectron field effect transistor and inverter. The also is called soliton solectron. Soliton in the chain in diacetylene and which carries electrons. So in fact, this is Davydov soliton. Very beautiful experiments are on the measurement of delayed luminescence from biological systems, where we have done several predictions which were nicely confirmed by the experiments. I don't have time to speak about these And in conclusion, I want also to mention that very important aspect, which has not been finished, in fact, and has important future, is the proton transport in hydrogen-bonded chains of water molecules. Then the ratchet of solitons in molecular chains, which can explain functioning of the biomotors, and a lot can be done here. The important part, the essential part of things which I've told you here have been done by collaboration, and I'm very thankful to Alexander Yeremko present here, to my colleagues in Durham, Jim Xilu, Bernard Piet, and Wojtek Zakrzewski, and to my colleague Manuel Velarde in Spain. So thank you very much, дякую, and Merry Christmas and Happy New Year. Oh yes, thank you very much, Professor Loktev, for your question about the future of Davidov solitons. As I already told you, I think that a lot can be done and should be done concerning the water systems, and I hope that the group of Sergei Volkov, Sergei Perepolitsa, who study hydration of DNA, hydration shells of DNA, can extend their research to take into account a study of the formation of soliton states in the hydration shells. Biomimicry technologies, so it's interesting not only from the fundamental point of view, but also from the experimental and study of the mechanisms and possibility of using external fields, electromagnetic, magnetic, electric, in therapies based on soliton mechanism is also very important. So I think that future, next 50 years will bring interesting results. Thank you. Thank you very much, Professor Sharapov. Question about the which experimental techniques can be used or are used for to check existence of soliton. As I already mentioned you, the Raman spectroscopy, especially some Raman spectroscopy with high resolution femtosecond resolution, which I already told you. I also mentioned the Hall effect to measure charge in electron transport chains. Study of the delayed luminescence, optical spectra. I think these are the study of the conductivity, which is now intensely carried conductivity of polydiacetylene of these biomimicry systems that are main techniques available now. Thank you very much.